Welcome back students to another session of chapter 10 light refraction and refraction. We were doing second part of this chapter, that is refraction, and in last lecture we studied about refraction. Now we are going to study about spherical lenses through which refraction is taking place. First of all, what is a lens? A lens is a curved device that is used to refract light. There are two types of lenses, concave lens and convex lens. Students, these lenses are made up of spheres of transparent material like glass, plastic, etc. And they are made in such a way that either their both surfaces are curved or one surface is curved. Here we are going to study the lenses whose both surfaces are curved. So now we know that lenses are of two types, concave lens and convex lens. What is a convex lens? A convex lens is a lens which is thicker at the center and thinner at the edges. You can see in the diagram, here at the center it is thicker and here at the edges it is thinner. It is a converging lens, which means that the light rays after refraction meet at a point. Next is concave lens. Concave lens is a lens which is thinner at the center and thicker at the edges. So in the diagram you can see that here at the center it is thin and at the edges it is thick. It is a diverging lens, means the rays after refraction through concave lens go away from each other. They cannot meet each other. So students, here you can see that how lenses are formed from the spheres made up of transparent material. Here it is not necessary that both these spheres are of same radius. They can be of same radius, they can be of different radius also. And since this lenses are made up of two spheres, they have two centers of curvature, C1 and C2. In most of the cases, C1 and C2 will be same if they are made up of spheres having same radius. So the radius of curvatures R1 and R2 will also be same. But if they are made up of spheres having different radius, then their C1 and C2 will be different and R1 and R2 will also be different. Here we will consider that the lenses are made up of same spheres of same radius. Now we will see different terms related to spherical lenses. Students, these terms are almost same with the terms which you have studied for spherical mirrors. Just minor changes are there. So let us see different terms. A lens, either a convex lens or a concave lens, has two spherical surfaces, and each of these surfaces forms a part of a sphere. This you are already knowing that lenses are made up of spheres, so they have two spherical surfaces. The center of these spheres from which lens is made is called center of curvature of lens. It is denoted by C. And since the lens has two centers of curvature, we will represent them by C1 and C2. And imaginary line passing through two centers of curvatures of lens, that is C1 and C2, is called principal axis. The center point of a lens is called optical center and it is denoted by O, whereas for mirrors it was called pole and it was denoted by P. Here it is denoted by O. Next is aperture. The diameter of refracting surface of lens is called its aperture, but we can't show it in the diagram since it appears on the outer part. Next is principal focus. A point on principal axis where rays parallel to principal axis actually meet or appear to meet after refraction from lens is called principal focus of lens. A lens has two principal foci, f1 and f2. And distance between optical center O and principal focus is called focal length and it is denoted by f1 and f2. Students, as we studied the rules for reflection through mirrors, now we are going to study the rules for refraction through lens. And these rules are same whether it is a concave lens or a convex lens. First rule is that a ray which is parallel to principal axis passes through F after refraction from the lens. Here in the first diagram you can see that a ray which is parallel to principal axis of convex lens passes through F after refraction, that is, it is passing through F2. In the second figure you can see that a ray which is parallel to principal axis of concave lens is getting refracted from the concave lens, and when it is extended backward, it is meeting at f1. Intersecting at f1. Second rule is a ray which is passing through principal focus after refraction becomes parallel to principal axis. So in the first diagram you can see that a ray is passing through f1 of a convex lens, and after refraction it becomes parallel to principal axis. In the figure B you can see that a ray is getting incident on concave lens through f1, and after refraction it becomes parallel to principal axis. Third rule, a ray which is passing through optical center O follows the straight path without suffering deviation, means it is not bending and it is following the straight path. You can see in the first diagram, a ray passing through optical center of convex lens is following the straight path without getting deviated. Similarly, in figure B also, it is following straight path without getting deviated for the concave lens. So these were the rules for refraction of light through spherical lenses. And now we will see the position of image, nature and size of image when object is placed at different places in front of lenses. The following table represents the image formed by convex lens when object is placed at different positions. First case, object is placed at infinity. Image will be obtained at f, that is f2. The size of the image will be highly diminished or point-like, and the nature of the image is real and inverted. Second case, when object is placed beyond 2f1, image will be obtained between f2 and 2f2. The size of the image will be diminished and the nature will be real and inverted. Third case, at 2f1, the image will also be obtained at 2f but on the other side, that is 2f2. The size of the image will be same as the object and the nature will be real and inverted. Fourth case, object is placed between f1 and 2f1. The image will be formed beyond 2f2. The size will be enlarged or magnified and the nature will be real and inverted. Next case, object is placed at focus, that is f1. The image will be obtained at infinity. The size of the image will be highly magnified or highly enlarged and the nature will be real and inverted. The last case is when object is placed between focus f1 and optical center O. The image will be obtained on the same side of the lens. The size of the image will be enlarged or magnified and the nature of the image will be virtual and erect. Students, here you can see that this table resembles to the table which you studied for the concave mirror. The only difference is for the mirror's center of curvature was represented by C and here it is represented by 2F. So if you remember that table, same table is here, just you have to make minor changes. Now let us study how to draw the diagrams. First of all, before drawing the diagrams, you should keep in mind that while drawing the diagram, the distance between O and F1 should be same as distance between F1 and F2. So first of all, we have to draw a convex lens. Now the object is placed at infinity, so the rays coming from the object will be parallel to principal axis. So consider the first ray which is parallel to principal axis. Here you have to keep in mind that refraction will take place from the center of the lens. So after getting refracted, it will pass through f2. Similarly, if we consider another ray which is parallel to principal axis, then after refraction it will also pass through f2, and you can see that they both are meeting here. So here image will be obtained which is point like. The nature of the image is real and inverted. Next case is object is placed beyond 2f. So here first of all draw a convex lens. Draw object AB anywhere beyond 2f. Consider first ray parallel to principal axis from point A. After refraction, it will pass through f2. So this is a refracted ray. Now Consider another ray which is passing through optical center O. It will follow the straight path without getting deviated, and you can see that they both are meeting here. So A dash is the image of point A. Corresponding to object AB, we will get corresponding image A dash B dash, which is obtained between f2 and 2f2. The nature of the image is real and inverted, and size is diminished. Here you can see that it is smaller than the object. Next case is object is placed at 2f. So first of all, draw the convex lens and draw object AB at 2f1. Consider a ray which is parallel to principal axis from point A of the object. After refraction, it will pass through f2. So this is a refracted ray. Consider another ray which is passing through optical center O. It will follow the straight path without getting deviated. So here A dash is, they both are meeting here at A dash. So A dash is the image of point A. Corresponding to object AB, we will get corresponding image A dash B dash, which is obtained at 2f2. So here the nature of the image is real and inverted, size is same as object, and image is obtained at 2f2. Students, in this diagram you have to be very careful. The size of the image should be same as the object, and image should be formed exactly at 2f2. Now the object is placed between f and 2f. So this is your convex lens. Object AB is placed anywhere between f and 2f. It is not necessary that it should be exactly between f and 2f. Consider the first ray parallel to principal axis. After refraction, it passes through f2. Consider another ray which is passing through optical center O. It will follow the straight path, and here you can see that they both are meeting at A dash. So A dash is the image of point A, and corresponding to object AB, we will get corresponding image A dash B dash, which is obtained beyond 2f2. The nature of the image is real and inverted, and size is highly magnified or enlarged. Another case is object is placed at principal focus f of the convex lens. So this is your convex lens, optical center O. Object AB is placed at f1. First ray which is parallel to principal axis. After refraction, it will pass through f2. Another ray passing through optical center O will follow the straight path. Now here you can see that they are not meeting because the image is obtained at infinity, that is very far, and its nature will be real and inverted, and size will be highly magnified. Now the last case, that is object is placed between optical center O and focus f. So object AB is placed between O and f. We'll consider the first ray parallel to principal axis. After refraction, it will pass through f2. We'll consider the ray which is passing through optical center O. Now here they are not meeting, so we need to extend them backwards. So first of all, I'll extend this ray which is passing through f2, and then I'll extend the ray which is passing through O, and here you can see that they both are meeting here, that is at point A dash. So A dash is the virtual image of point A. So corresponding to object AB, we will get image A dash B dash, which is virtual and erect and magnified. The following table shows the image formed by concave lens when object is placed at various positions. First case is object is placed at infinity. The image is obtained at focus f1. The size of the image is highly diminished or point-like, and the nature of the image is virtual and erect. Second case, object is placed anywhere between optical center O and infinity. The image will be obtained between f and O, that is f1 and O. The size of the image will be diminished, and the nature of the image will be virtual and erect. Now students, here only two cases are there, because if you will keep the object anywhere between O and infinity, you will get the image as virtual and erect. Its size will be diminished and it will be obtained between O and F1. Now let us see how to draw the diagram for image formed by concave lens. So first of all, you have to draw the concave lens. This is optical center O. Keep in mind the distance between O and F should be equal to F1 and F2. Now we'll consider the first case in which object is placed at infinity. Since the object is placed at infinity, the rays coming from the object will be parallel to principal axis. So consider the first ray which is parallel to principal axis. So it will get refracted like this way, and when it is extended backward, it is passing through F1. Similarly, we'll consider the another ray which is parallel to principal axis. It will get refracted like this, and when it is extended backward, it will be meeting here. So here you can see that they both are meeting here. So it is the virtual image of the object which is highly diminished or point-like. Now the object is placed anywhere between O and infinity. You can keep the object anywhere. The nature and the size of the image will be same. So first of all, draw a concave lens. And draw object AB anywhere between O and infinity. Consider the first ray which is parallel to principal axis. It will get refracted like this, and when it is extended, it will meet at F1. Now consider another ray which is passing through optical center O. So here you can see that these both rays are meeting here. So this A dash is the virtual image of point A, and corresponding to object AB, we will get image A dash B dash, which is virtual and erect and diminished. So this was the image formed by concave lens when object is placed anywhere between O and infinity. So students, in this lecture we studied what is a lens, types of lenses, terms related to lenses, rules for refraction through lens, table showing images formed by convex and concave lens, and the ray diagrams for concave and convex lens. With this, we conclude our lecture. Draw these diagrams in your notebook and practice them many times, so that if it is asked in the exam, you can score full marks in drawing the ray diagrams.